All right, let's get started. How's everybody doing out there? Having a good SAINTCON? All right, we have some woos. That's always good to hear instead of dead silence. So I'm Chris Mather, and my presentation is on quantum cryptology Armageddon. Now don't worry, I'm not going to get too technical. I am not a quantum physicist, so you should all be able to keep up. These are the topics we're going to be going over. We're going to give you some quantum basics, so you can kind of know what we're talking about a little bit, understand the molecular level of things. Then we'll get into quantum cryptanalysis, the offensive side, quantum cryptography, the defensive side, and then we've got some goodies, some things that you can play around with. And then I've got references, so you guys can check this out later. I don't have the slides of this per se posted on the SAINTCON repository out of slide deck, but I'm trying to get a URL there that you guys can go and check this presentation out later, and also for the references, the links to things, so you can check that out. So let's dive right in. Armageddon. So quantum computers. People have been talking about the threat of those. They're going to be able to crack all of our codes, and the internet will just, fall apart because nothing will be secure anymore. So we're going to start out with a little video to get us in the mood.
Bish, I think you better come over here. Carl, you got your little black book?
Yes.
Give me the number for something impossible to access.
Okay. What about this? Federal Reserve Transfer Node, Culpeper, Virginia.
That's your good luck.
900 billion a day goes through there.
That'll do. Punch it in.
Okay. You won't get in. It's encrypted. See?
Mother, that last contact. Look at this, boys. Anybody want to shut down the Federal Reserve?
Hey, don't screw around with that thing.
Carl, what else you got?
National Power Grid. Okay.
Here we come. Hey, Mother.
Rolling.
Wow. Unbelievable. Anybody want to black out New England? Carl, what else?
Air traffic control system.
Okay, Mother.
Oh my God.
How is this possible?
Cryptography systems are based on mathematical problems so complex they cannot be solved without a key.
Janik must have figured out a way to solve those problems without the key, and he hardwired it into that chip.
Turn it off.
Anybody want to crash a couple of passenger jets?
I said turn it off. Turn it off.
So it's a codebreaker.
No. It's the Codebreaker. No more secrets.
So that is the threat that quantum computers are bringing, or that's what a lot of people believe, that quantum computers will be this supercomputer that can just break through all the codes without any problem because they will be so fast. That is called, there's something called quantum supremacy. And that is the point at which quantum computers will have the processing power and ability more than what our conventional systems have right now. And they're kind of measuring that in qubits, you know, how many bits their quantum computers have. There's estimations between 60 to 100 qubits is what quantum computers are going to need to reach that quantum supremacy. But it's kind of a moving target. The traditional computer scientists are increasing their algorithms and things to kind of raise the bar for the quantum computers to reach. And so it's kind of a fuzzy line, but it's soon approaching. So there's a concept called hack and wait. So we've got these quantum computers that aren't here yet, but there are nation states, ours included, and others that have collected our encrypted information, and they are just storing it. So they know that even at the time they collected it, the computers they had couldn't crack it. They know technology is increasing and increasing. We're getting better GPUs, and those will enable them in the future to crack those codes. And can we switch over to just the microphone? Yeah. Darn thing didn't want to stay. All right, we're still good? All right. A little less distraction. So yeah, so nation states and other people have collected these, they've hacked into systems, collected passwords and such information that they can't crack. But they're just holding on to it and waiting for the day when either their traditional computer resources or quantum computers will be able to break those open and get to the secrets inside. So along with that, the United States just recently, Congress, I think it was just this month, passed the National Quantum Initiative Act. They are setting aside $1,280,000,000 over a 5-year period to invest in quantum technology, quantum research, and into the quantum realm. They're realizing that this is a big thing and we need to get involved in it. They've been involved in it, but not as much. And China is investing a lot of money. We're behind them. So the United States is trying to up their game a bit and catch up. I think it's kind of interesting that the budget number starts with 128. I think a computer guy kind of had something to do with the financing on that. So that's the doom and gloom that's coming. So let's look at some of the basics of quantum mechanics. So we're going to talk about quantum particles, what they are, and then 3 concepts that are important to understand quantum computers and the things that we'll be talking about. Those are superposition, particle spin, and entanglement. So jumping in, if y'all remember from school, your physics class, atoms have particles within them. Those would be the electrons, the neutrons, and the protons. And we've also learned that the protons and neutrons have quarks as well, or that's another particle. So the quantum mechanics is the study of these smallest particles and their behaviors and how they interact. Most of the stuff that they deal with in quantum physics is the electrons, manipulating and working with electrons. They don't use protons, neutrons, or quarks so much. The electron seems to be the one they like. But there's also photons. Now, it was traditionally the idea that light is a wave. It's not a physical particle like things we have. But they've learned that photons actually have a physical component. There are light particles, and also that the other one, particles of matter, exhibit behavior like waves, just like they figure light did. So they're a little bit of a blend, but kind of the big takeaway is there's 2 kind of particles that you'll encounter if you read about quantum mechanics. Some systems use the electrons, but others actually use photons to do the things they do. And we've got a couple examples of that. So those are kind of the basic ground level components we need to work with. Superposition. This is kind of what gives quantum computers their power or their magic. So traditionally in computers, we have ones and zeros. Our bits, we can turn them on and off. And that's how we create our numbers and do all our calculations. Quantum particles can behave as if they have multiple states at the same time. So they can be a 1 or a 0, or they can be a 1 and a 0 at the same time. This is kind of due to the positioning. You can see our little diagram here. The coordinates or the spin of a particle. So it can exhibit multiple values at the same time. And that's one of the important things for qubits in quantum computers is how they can be so fast. Particle spin. So these particles, if you sustain an electron in a magnetic field, it'll have a spin. And scientists have learned to control that spin and read it. If it's spinning with the magnetic field, they call it spin up state. If it's spinning against the magnetic field, it's spin down state. They use lasers to read and change the spinning states of these quantum particles. And we'll see later on how that gets used in quantum computing, but that's another one of the concepts you need to understand. Entanglement. You may have heard about this one. It's where you take two electrons, or two particles, they could be photons, and you entangle them together. They are joined by some kind of force. And you can move them apart and separate them, and when you change or read one, the other one will react as well. And that's kind of what they call information teleportation. So yes, we have discovered teleportation. Yay. And it used to be when they started this, the particles were very close together. They weren't very far apart. They were like, first couple experiments was like millimeters apart, and then they were able to increase it to centimeters. And they just keep growing that distance that they can keep those particles separated and transfer that information. And so that's called entanglement. I don't know if they've figured out exactly what that force is that joins the two. Sometimes they call it spooky physics or magic, but those particles can be entwined and read and send information to the other. So those are our physics basics that we kind of need to know. So let's jump into cryptanalysis. This is the attacking side. We're going to talk about the qubits, quantum computers, and then some information from NIST and the NSA on how they feel about this and their recommendations, and the rest of the industry where they're at. So we know classical bits are a 1 or a 0. Qubits can be a 1 and a 0 at the same time, like we talked about. If you can see the little picture here, little mouse. This is a quantum computer CPU or chip, and each of these little square boxes with the equal signs in them is where an electron qubit is being suspended and used. So this right here, we've got a 2, 4, 6, 7 qubit CPU. Now, the way the computations work on it is you can have 2 to the n computations per qubit simultaneously. So the number of qubits is the n. So let's say we have 100 qubits. You could do 2 to the n, or 2 to the 100th power of calculations in one step. And that's that number there at the bottom, which if you spread out, that is pretty darn big. I mean, we talk about, you know, our GPUs that we have, our 1080 Ti's can do, you know, so many millions of hashes in a second. This is exponentially bigger than that. Now this is just kind of one calculation, one CPU cycle. So you'd still need to develop your quantum computing algorithm to process, you know, do something like hashcat or like that. But that shows the power of quantum computers. That is the threatening, scary part. But it's also the cool part, because quantum computers aren't just going to be used for, you know, hacking passwords, even though that's what we're talking about today. They're looking for them to do artificial intelligence things, look into chemical modeling, giving us new materials, and all sorts of applications. So quantum computers are not bad, but there's a side we have to deal with. All right, this right here is a quantum computer. That's what they look like. These must be super cooled. So I don't know all the wires and things, but the little electrons that they use have to be in a super cooled state for them to work with them. A lot of degrees below zero. I don't think it has to be absolute Kelvin zero level. And the quantum computers isn't just a computer all by itself. They have to work in tandem with a normal computing infrastructure. Kind of like our current GPUs. They'll have the traditional computer where you kind of set up the things and you pass your quantum algorithm over to the quantum computer. It does its fast calculations and math and brings you back the result, and you continue on with your project. So kind of in that respect, quantum computers will never become personal computers. We won't have a quantum computer sitting on our desk or carry one around in our pocket. I know we think about technology, well, you know, our traditional computers used to be like a mainframe in a room, and then they, you know, it came to the Apple computer that we could put on my desk, and now they're on our phones and on our watches. But just kind of the physics behind quantum computers will prevent that from happening. I'm sure they'll get smaller, but yeah, we'll never have one at home. Unless you count cloud computing. So there are quantum cloud computing services that you can sign up for and play with. And that will probably be the methodology that most of us will have to interact with cloud computers, or quantum computers. We'll be able to access them through the cloud, send them our calculations, and get results back. And we've got some examples of those at the end. So NIST has come out with a report. We call it a report on post-quantum cryptography. And they basically assessed the threat of quantum computers. Now, this was back in April of 2016. I haven't been able to find any kind of updated references, or more so. But kind of like, I guess, our OWASP top 10, 2013 existed for like the longest time until just last year they finally did an OWASP top 10, 2017. So, but as you can see, we'll zoom in a little bit. They've given some, I don't know about recommendations, but what they see the quantum computing will do to our current algorithms. Near the bottom you can see all of our public key algorithms are totally threatened by quantum computing. They will no longer be secure to use. RSA, elliptic curve, DSA, those are very vulnerable to quantum computers and the speed of the calculations they can do. Our other encryption stuff, like AES and the SHAs, or encryption and your hashing, are a little more resistant to quantum computers and the power that they bring. We can increase our key sizes and make them resistant to quantum computers. So we'll move on to what the NSA recommends. And again, this is a report from 2015, kind of the latest I could find that they've recommended. But they give some recommendations that you can do right now. If you've got a system that you're doing encryption with, your files for your company or something, look at bumping up your encryption levels. Because quantum computers may not totally be here right yet, but like I said, there's the problem of the hack and wait. If you get breached now, they'll just wait a couple years till quantum computers are there, and then they can open up your stuff. So as you can see, the NSA recommends, like for example, AES, use 256-bit keys, and they say that is good enough to protect top secret. This is government stuff. So if you feel your company's files are top secret level, bump your stuff up to 256-bit encryption. Even if they're not, bump it up anyway. We've got the references for the different publications like the NIST and the FIPS, if you wanted to read more on those and what to do with them. They've got some, so we've got the RSA, we've got some elliptic curve in there, and they recommend bumping up to P384 and down to the RSA minimum of 3072-bit modules. So you can protect yourself right now from quantum computers when they get here. These will be in the slides that you can get later on, and also I've got the reference links to these documents so you can read more about these, the NSA and the NIST recommendations. So that's kind of what we can do right now to help prevent things or data from being breached by quantum computers. This is where the industry is right now in their progress on developing quantum systems. D-Wave was one of the first companies that really got into quantum computers and proved, yeah, we can do this. This is real stuff, not just theory. As we mentioned, quantum supremacy is estimated for between 60 and 100 qubits. And as you can see, we're in the zone. We're closing in on that. Google recently, this year, bumped their quantum computer up to 72 qubits of processing power. Before that, IBM held the title at 50 qubits. I'm sure they're working on bumping that up further as well. I don't know as of today where things are, but that's the latest I've been able to find. Now, D-Wave, you look at them and you go, whoa, they've got 2,048 qubits. They've like totally surpassed quantum supremacy. It's a little different. Their system is an annealer. Now, I don't know exactly what an annealer does. I've read about it several times. I still don't totally grasp it. But it's kind of a specialized quantum computer. It does specialized tasks. So it's a little different than the Google and IBM ones that could be used for like quantum cryptography. There's another company called Rigetti. They are predicting, they're estimating, in a year they will have a 128 qubit computer. And this was just a month ago is when they made that estimation. So it's at the doorstep, it's coming. China has definitely seen that this is coming. We'll zoom into that. And they are putting resources and money into the quantum field. Here's a chart compared to China versus the US. US is the black line, China the red. And they are putting a lot of money into quantum technology, getting patents, and developing their quantum infrastructure. And the US, not so much. Now this chart doesn't include the initiative that was just recently signed. So hopefully we're bumping things up a little bit, but we do have some catch up to do. And that's where the industry sits. There's other companies out there, but these are the ones I was able to research and present to you, and kind of the leaders. All right, let's dig into what we can do about this to defend ourselves in cryptography. So they're working on new algorithms that are resistant to quantum computers. And we'll also go over some other technologies, particle key generation, and how that is like totally unhackable. Well, not everything is hackable, right? You can always hack something. And then we'll go over applications of entanglement. So here's a list of some of the new algorithms they're working on. One of them is called lattice-based. You see the picture over there with the, it's kind of like a layer of grids, and using that to perform different calculations. That is resistant to quantum computer power. Also, multivariate polynomial cryptography. That's all this algebraic math over here that I don't understand. That's another one. Super singular elliptic curve isogeny. Doesn't that one sound fun? That one's all these little squiggles here. Those are different elliptic curves and doing calculations between multiple curves. So some of these algorithms, they've figured, well, we'll just fight fire with fire. Well, if you're going to crack our codes with a supercomputer, we'll use a supercomputer to calculate them. And so it just brings it up to that level. And some of these algorithms are planned for that usage. Your standard normal computer would not be able to crank through these and be useful. So some of these they're being designed to be used on supercomputers. We'll skip down. Hash-based is using hashes to do digital signatures. And code-based is using error code correction values somehow to create encryption. The middle one here, symmetric key quantum resistance, is what we talked about previously. Using our current encryption systems like AES and stuff, and just bumping up the level of bits we use. That has proven effective against the power of quantum computers. And so we can use some of the algorithms we currently have in a quantum world. So we're going to give you an example here of generating a key using quantum particles. So in this case, we're going to be using photons. As I mentioned earlier, the quantum computers and the chip I showed, that one used electrons to do the quantum mechanics. In this case, we use photons. So what we have here is these photons are going to have spin. Remember spin, we talked about that. In this case, we have rectilinear spin, which would be up and down or left and right. And then we have diagonal spin, which would be to the upper right or the upper left. Now we're going to have Alice and Bob, and Alice is going to send Bob a key. And she's going to do that by firing photons at Bob. And so she's going to generate a whole bunch of these photons and basically create a bunch of ones and zeros, a key. And she's going to do that at random. And she's going to use 4 different filters here. So we've got an up and down, a left and right, and our 2 diagonals. And she'll swap between the 2 different schemes and the 2 different values, just randomly firing photons over it at Bob. Now Bob is going to use filters to read those photons coming at him. Now his filters look like the ones here on the bottom. So he's combined the up, down, left, right into one filter. And then the 2 diagonals are combined into a filter. So he's going to pass that photon through his filter and read it. So if it's a rectilinear filter, if it's up, he's going to get a 1. If it's sideways, he's going to 0. If he uses a diagonal filter, he'll read the diagonal spins and get his 1 or 0 that way. However, he doesn't know which filter to use, whether to use the rectilinear or the diagonal. So let's say Alice sends an up and down spin photon, and Bob uses the diagonal filter. He is not going to read that photon correctly, and it will change the spin of the photon as he reads it. So basically, half of his reads are going to be wrong. The Heisenberg uncertainty principle kind of dictates that the particle he's going to read, he's not going to know which filter to use, and when he reads them, he's either going to get it right or it's going to be screwed up. So half the values are going to be bad. But that's okay. So the way they've worked around that is now, once Bob has received the bits, he calls up Alice and says, hey, what was our filter scheme? And she'll say, oh, I used a rectilinear, a diagonal, a diagonal, a diagonal, a rectilinear, a diagonal. And that way he can go, all right, now I know which of my bits are good, and they can both agree on, all right, here is our encryption key that we're going to use. And that's how that works. There's a great video online that kind of walks through it. I went through several of them. A bunch of them didn't kind of really make sense until I found one that oh, it clicked. It's like, yeah, that one's good. I've got that in the references for you guys, so you can go through this. Now we're going to throw Eve into the equation here. And we're going to kind of show how this is impervious to eavesdropping or man-in-the-middle attack. So let's say we've got Eve sitting in the middle, and she's seeing these photons pass by too. Now, if she measures one with a bad filter, she's going to get the wrong result. And it's going to change the spin of it that Bob's going to get. So half of her guesses will also be wrong because she doesn't know which filter to use. She's got to do the same thing that Bob did. Swap between rectilinear or diagonal, just take a guess and like, I'll try this one. So half of them are going to be wrong. Now you say, all right, but she can listen in on the conversation between Alice and Bob afterwards and get the schema, right? Which she can, but it won't help because she will get a different set of filters that she used compared to Bob. And so even if she listens in on the filter scheme of the rectilinear, diagonal, rectilinear, it's not going to help her because she did different measurements than Bob did. And so her scheme that she would come up with, like, oh, here's the key, is going to be different than Alice and Bob really agreed upon. Part of the trick of it is doing that measurement beforehand, and then afterwards, okay, here's the filter scheme that we used. So this is a way that they're using quantum particles to generate keys that are impervious to eavesdropping. There is a company here in the States called Quantum Exchange that is using this technology. They have a system for that. They have an endpoint, and they send a key to another endpoint using this technology. And so any man-in-the-middle attacks are useless. One of the problems, though, is that distance thing. Remember, the particles can only go so far. The problem with that is when they shoot the particles, there's the chance that particle will hit another particle in space or in the fiber optic cable or whatever medium they're transmitting these particles and bounce off or get wiped out. So that distance thing has been a problem. And kind of all the particles that just exist in the medium they're using. And so to send a message, you have to send to one relay point, get the message, re-encrypt it, send it to another relay point, and down that way. So I know all the hackers are going, there's the target. Hit the relay points, right? You know, I can't figure out what the message is in transition, but if I can, get some code in there at the relay point, that's where I can read it. And that's true. That's one of where the weak spots are. China has done a similar thing. They actually have a network between several of their cities that uses this technology. And they are increasing the distance that they can send things, so they're starting to reduce those endpoints, those nodes, and increase their security level. They're also using another scheme, which is pretty cool. They are starting to use satellites. So they've got a satellite called the Mycius satellite. And this has helped them with that distance problem. So they figured, well, if we're transmitting these particles and it's hitting all the air and whatever particles we have here, let's throw it up into space where space is empty, right? There's hardly any particles there that are going to interfere with ours reaching its destination. And they originally did this between a couple of cities in China. And this is a little bit different schema than what we went before, but kind of the same principle. So they have the satellite, and the satellite creates two entangled particles. Shoots one down to one city, shoots the other down to the other city. And now these two cities have entangled particles. The one city will read the one, and it'll change the value of the other, and they read the value of its paired particle on the other side, And we have just sent a message between those two particle bits. And once again, this is entanglement. There's no medium between. There's no way to, guess what that change was. It's just there. So teleporting information. I've read some more, and China has increased their ability with that. They've actually set up a system, a receiving station in Vienna, near Vienna. So yeah, they can send a message between Beijing and Europe using their quantum satellite and these entangled particles. So they're learning to increase that distance. And if you think about the technology it takes to do that, you've got a satellite orbiting the Earth, miles above the Earth, and you're shooting a subatomic particle down to a receiver station and hitting their receiver and measuring that. It's pretty amazing. And right now, in the United States, we don't have anything like that. We just have kind of the land, ground-based systems, but I'm sure we're working on it. So those are some of the things, the methodologies we're using quantum computers and particles in defense. So we're going to jump into some of the quantum goodies, things you guys can actually play with. So Microsoft has developed a quantum computer language. They call it Q#. You can actually go to their website and download the development package and install it into Visual Studio. And I'm sure you can install it in kind of other development systems. They've got a link there for Windows and also Mac OS and Linux. And you can start learning quantum computer programming language. And I don't know if you can use it on a quantum computer yet, but you can get a feel for how the mindset of programming a quantum chip works. It's a little different with the whole superposition structure, and things can have a 1 and a 0 state at the same time. But that'll give you an introduction into that if you're interested in going into the quantum field and getting a future job as a quantum software developer. Sounds cool to me. IBM, they have a quantum computer you can go and play with right now. They call it their IBM Q Experience. They used to have 3 bits, they've bumped it up to 5, but you can go to their website and you can log in. They've got tutorials there, a bunch of things that'll walk you through how to program a quantum computer. And it's an actual quantum computer they have. Right here, it'll kind of show you, you've got this one's a 5-bit quantum computer. There's your bits, their values, and down here is where your program will be. You add these different gate structures and things and create your calculations. And you send it over, and it actually runs on their quantum computer, and you get back the results. So you can actually go and play around with a quantum computer now. Sounds pretty cool. I've read some of the things. There's a guy, he created a little game that he plays on the IBM quantum computer, a little quantum computer game. So the technology is here right now, and you can be using it. Rigetti, they have a similar system. I haven't dug into it too much, but they have a quantum cloud service that is in beta right now, and you can sign up for the beta and play around with their quantum computer. Entanglion. Now this is a game that was actually kind of developed by the IBM people. And it's a board game that teaches quantum computing concepts and things. So you can learn kind of in an easy way the ideas and concepts of quantum computers and how they work. It's shown here in kind of a nice little boxed set, but it's actually an open source thing you can download from GitHub. We got the link there. And I guess you can print it out and play it at home. And it's a kind of a low enough level. Got the hashtag there, checked out some tweets, and one lady said, "Oh yeah, I played this game, my 10-year-old loved it." So it's not a high-level complicated game. If 10-year-olds can grasp it, it's got to be good. And I haven't downloaded it yet, but I want to. Check it out and play that. So that'll help teach you some of the concepts of quantum computers in the easy way. Or get your kids involved. Get them a jump on technology. So those were all the goodies. That was my presentation. Here's the references. I don't expect you to try and write these down right now. I do have them posted online so you can download. You can't download this presentation, but you can go to and check it out and get those. So up here I've got some links for the quantum basics, get you into the quantum physics. There's a lot of stuff out there to read if you want to learn more. The quantum cryptanalysis, I've got the links for the NIST publication and then also the NSA recommendations. And some other things on Defense One and the quantum computers, where they're at. The cryptography, Wikipedia has a good article on those different algorithms, like the lattice and the supersingular isogeny one. There's the YouTube video on that particle key generation technique, and some information on the Messier satellite, and links to the goodies. So down here at the bottom, whitecapcyber.com/2018 SAINTCON. That's where you'll want to go, and that'll bump you over to the presentation, and you can flip through these slides on your own and get the references and check things out. That's my presentation. Any questions? Yeah.
The entanglement, is that satellite required?
No.
Or once they've been sent,
So they started ground-based. Like I said, they were able to entangle particles, but they were only like, a centimeter apart. And they've learned to, get those particles further and further apart. The problem was, as they got them further apart, they kept bumping into other particles, right? And so they do have a ground-based system that works, but they figured, hey, let's throw it up in space, and that way there's not all those other particles we're gonna bump into. We can get our distance further away. So you don't have to use a satellite for that, but they've figured out that works really good and helps them overcome that distance problem.
because there's not a lot of particles out there.
Yeah, right. Not until you get kind of down the lower levels of the air and atmospheres where you might bump into particles and stuff that will throw off your entanglement. Good question. Any others? Yeah. Right. I'm sure we'll still use passwords. I mean, we keep trying to get away from them, but they're still there. The quantum computers, I'm sure the NSA and I'm sure China and Russia are looking at those going, hey, we need to, these are going to be our methods to break the other guy's passwords and stuff. So I'm not sure how much it's going to be, Armageddon or not. As you noticed, the encryption methodologies weren't too vulnerable, but our public key encryption schemes were really vulnerable to the quantum computers. I'm not sure how much our passwords will change. We may have to bump them up to more characters. Your passwords will have 60 characters in them now instead of 20. Does that answer your question? Enough so? Any others?
Yeah, what's the speed on the entanglement setting?
The speed?
Teleport thing, yeah.
Instantaneous. Yeah. So, I mean, you send the particles once you get them there. Yeah. And then when I read this one, that one changes.
Could you have one on the moon and then far away and it would be...
If we could build a particle receiving station on the moon to receive it, maybe, I don't know. But yeah, they're working on that distance thing.
And it's faster than light? It's just the same?
Yeah, it's magic. They call it spooky physics. You just change the one particle, and the other one over here just changes instantaneously. I don't know if they know what is connecting them, what force, but there's some kind of force. They're able to entangle the two together, split them apart. You change one, the other one changes, I think, to the opposite value that you did the other one.
That's all theory, right? Or
No, they're doing it. They are that satellite that China uses does that. It does that entanglement and information teleportation. Anybody else? Yeah, in the back there. Right. Right, yeah. You know, anything's possible, but the science they're doing right now, they don't even know the force that's between them, right? So I would say there's nothing in between you could do to affect these, but thinking like a hacker, I would attack the receiver station, right? Attack them there. You can't man in the middle that, but I can attack the receiver station and find out what they read there. Yeah, maybe. We'll find out. And maybe there's nothing we can do about it. It's like, well, we know what the force is, but it just is. We can't do anything with it. Any other questions? All right, that looks like it. Thanks a lot.